let us start. Enterprise network architecture. Now we'll be covering in this chapter hierarchical LAN design model. There are different design models, so we'll be covering the different design models, like what is hierarchical LAN design model, what is enterprise network architecture. Okay, in this section we'll study about these topics. Okay, just give me a moment. Okay, so hierarchical LAN design model and enterprise network architecture options. What are the options available for my enterprise network? Okay, so we'll start with hierarchical LAN design model. Now, hierarchical LAN design model, as the name only says, we will be having in hierarchy. Okay, we'll be having an hierarchy for the models. Okay, so hierarchical LAN design model divides the enterprise network architecture into modular layers. Okay, now modular layers allow each layer to implement specific functions. Modular layers can be replicated throughout the network, providing scaling and consistent deployment method. Provides fault containment. Okay, then provides the ability to put network components in place or take them out of service with no impact on the rest of the network. Okay, so we can scale our network. We can, you can say, we can see some faults if there are any faults in the network. This layers will give me a distributed things. Okay, like I'll be having a complete network distributed in different layers. Okay, so those layers are distributed in this way: access layer, distribution layer, and core layer, also referred as the backbone layer. Okay, so these are the layers that are distributed, and we'll see one by one what are the workings of. And the right hand side you can see a diagram, a small diagram for the different layers. Okay, so access layer is something like it you can say it is also known as the network edge. Okay, where my end devices or users are attached. Okay, like PCs, IP phones, wireless access point, printers, or you can say IP cameras. These all things are attached at this access layer. Distribution layer is something known as aggregation block. It aggregates access layer switches in the building or campus. Okay, so you can see over here in the diagram, it is aggregating. Aggregating means it is taking to one point. All the access layer switches are going to one point. Okay, at the distribution layer. Now we are having two distribution layer switches for redundancy. If my one fails, then I have another one. I have another one for redundancy purposes. So distribution layer aggregates the access layer switches in the building. Okay, then comes core layer. Now core layer is something like the backbone and aggregation point for multiple networks. It is an aggregation point for multiple networks. It provides high speed layer 3 connectivity. Okay, it will provide you high speed layer 3 connectivity. Got it? So we'll see about all of the layers in details. Now, like scalable layer design is somewhat like this. Like if you have a small enterprise network, if you have a small enterprise network, see, I'm using a mouse, I'm not using a pad. So this will be, the handwriting will be somewhat like this only. Okay, I'm not having a good handwriting. So if you're having a small enterprise network, then what you can do, you can just make the core and distribution layer as on one particular layer. You can combine the core and distribution layer. Okay, and you can have a separate access layer. Now if in future suppose you have another building and you want to connect that building with the network, then what you can do, you can scale your network. And what you can do, suppose this is your building 1 and this is your building 2. Okay, now you want to scale your network from one building to 2 buildings. So what you can do, you can separate the disk core layer and you can have a separate core layer over here for better performance, because your network has been increased. Now you are having a huge network, you are having a huge enterprise network. Okay, so what you can do, you can just connect. Now this distribution layer will be responsible for the first building, and this distribution layer will be responsible for the second building. But overall network will be going, these two networks will be going and joining with the core layer. Okay, and the core layer is then in turn connected with the WAN connectivity, or you can say it is connected with the internet or somewhat data centers, anything outside the network. Anywhere outside the network, the core layer will be connected outside the network. Any of the WAN connectivity, or any of, if it is connected over the internet. Okay, so it can be connected over the internet also, it can be connected over the data centers also. So like this, in this way you can just scale your network, scalable LAN design network. Okay, scalable layer design network, you can say. Now number of layers depend on network deployment characteristics. Like example, I told you a single building may require only distribution and access layer. Okay, you can say, you can call this layer, this type of network as, you can call this as two-tier design or collapsed core. You can call it as collapsed core network. Okay, so if you are having a small enterprise network, then you can have this collapsed core. And as the network begins to grow, core layer is required, okay, to scale out. So scale out means add more boxes horizontally. As I've added in the diagram, I've added more boxes horizontally. And scale up means increasing the capacity of individual box vertically. Okay, so I have added more boxes horizontally, and scaling the capacity vertically means this is something means scalable. Okay, so this type of network is also known as collapsed core, in which we are having, or you can say two tier collapsed core, in which we are having the core layer and distribution layer at one, they are collapsed with each other. Then we have access layer. Now what is the use of access layer? The access layer, also commonly referred as the network edge, is where your end devices are connected or endpoints are connected to the network. As I told you, it provides high bandwidth device connectivity using wired or wireless. So it can be either wired or wireless, both. Access technologies such as gigabit Ethernet and 802.11n, 802.11 AC wireless. Okay, so these are some technologies that it can use at the uh, access layer. Okay, so you can see these are the access layer devices that are there in the diagram. This is my access point, this is my something IP phone, PC. Okay, all the devices are there over here at the access layer. Devices are attached: PC, IP phone, wireless access point, printers, IP camera. Okay, now here we are having first hop. This is the first hop for quality of service trust point. This access layer is the first hop for quality of service trust point. Okay, now access layer can be logically segmented using VLANs. Like we can use different uh, logical network for performance management and security. We can do communication between access block that occurs through distribution blocks. Okay, Access switches are connected north and south to the distribution, and access switches are not connected east to west to each other. As you see in the diagram, access switches are not connected to each other, but they are connected in the north with the distribution switches. Okay. So basically access layer is a layer where my devices are connected. Okay. And at that layer, I can segment my network into VLANs using my VLANs. Okay. I can make logical network for better performance and better management and security. Okay. Then comes distribution layer. Okay, now as I told you, the distribution layer it aggregates access layer switches in a building or a campus. Now, whenever it aggregates, it reduces the number of cable runs. It is reducing the number of cable runs. No daisy chaining of access switches. Okay, so normally it provides a boundary between layer 2 and layer 3. It will provide you boundary in the layer 2 domain and the layer 3 core 3 core layer. Okay, it will be a boundary. Okay, and distribution layer switches interconnect to each other with layer 2 or layer 3 links. Like if I go back in the diagram, you can see in building one side you are having a two distribution layer switches, and they are connected with each other. Okay, now layer 2 spanning tree protocol down to access layer, and layer 3 routing up to the core layer. Okay, so here they will be running spanning tree, and between the core layer and the distribution layer will be running some routing protocols. Okay, we'll be running some routing protocols between the layer 3 routing up the core layer. Now this is the logical place for summarizing IP addresses space upstream to the core. Okay. Now this boundary, the boundary between the core layer and the access layer, it will provide you some functions for LAN. Okay. On the layer 2 side, the distribution layer creates a boundary for spanning tree protocol, limiting propagation for layer 2 faults. If there are any layer 2 faults, it will be removed. On the layer 3 side, the distribution layer provides a logical point to summarize IP routing. Okay, information when it enters the core of the network. So whenever you are using summarization, okay, so to the distribution layer is responsible to summarize your network and send it to the core layer, because core layer will be getting different networks. Okay, now the summarization reduces IP routing tables for easier troubleshooting and reduces protocol overhead for faster recovery from failures. As we all know about summarization, what is the use of summarization? Now distribution switches should be deployed in pairs for redundancy. Okay, like we can use SSO, stateful switchover, supported in chassis based solution. Okay, we can use now this is something distribution layer connectivity. I have two diagrams. Okay, distribution layer connectivity for different networks. Okay, now when campus buildings are geographically dispersed, distribution layer switches can be located within the buildings in order to reduce the number of fiber optic runs, which are costly between the buildings. Okay, so either we can connect in this way, or we can keep it in this way, like we can keep them in a building and we can connect the distribution layer switches. So distribution layer switches interconnect to each other with layer 2 or layer 3 links. Then comes my core layer. So any doubt till here, guys? Access layer and distribution layer. Okay, thank you very much. Now comes my core layer. Core layer, you can say, is a backbone and aggregation point for multiple networks. Okay, now as our network, as I've written over here, as the network grows beyond three distribution layer in a single location, organization should consider using a core layer to optimize the design. Okay, it will provide you high speed layer 3 connectivity. The core layer is the backbone and aggregation point for multiple network and provides scalability, high availability, and fast convergence to the network. Now the core can provide, as I told you, the core can provide high speed layer 3 connectivity between the distribution blocks, between the WAN, the internet, the data center, the network services. Okay, it reduces the cabling needs from n into n minus 1 by 2, okay, to n links for distribution switches. These is some calculation that can be done. Okay, now what do you mean by network? You know the distribution blocks, like we have distributed, you know, the WAN, the internet, the data center. The network services layer, where we load balance our traffic, where we can load balance our traffic, or where authentication is done. Okay, the network services layer where the authentication is done. So this is the work of core layer. It is responsible to provide you high speed layer 3 connectivity, okay, between the distribution blocks, between the WAN, like if I'm connected with the WAN connectivity, then over the internet with the data center. These all things are done at the core layer. Okay,
Here the last point, it reduce cabling needs. Can you explain more on this?
come again, I cannot hear you.
Can you explain more on this n into n minus 2 to n links switch?
See,
How the
these are
links will
some
be?
formulas that are, this is some formula, you can say, n into n minus 1 by 2 to n links for distribution switches. Okay, so
No,
the links that are
core
connected
layer.
from the,
Okay,
yeah,
go ahead, please. Sorry.
come again.
No, no, continue. You complete.
See, the links that are connected between the distribution layer switches and the core layer switches. Okay, so it is something formula that is calculated on the basis of how many links are uh, calculate how many links are there between the distribution layer switches and between the core layer switch, between the core layer and distribution layer switches. So this is the formula. Okay, so
Yeah, I got this. So let's say we have 5 routers in core. So the 5 routers will be connected in full mesh, or it will be how the connection happens generally in production network.
see, they will be connected in full mesh, like you can see in the diagram.
So full mesh require 5 into 4 by 2, like n into n minus divided by 2. Full mesh
Yes,
formula is this, right?
yes. Okay, n into n minus 1 by 2. Okay, n minus 1 number sum of n minus 1.
Yeah, I got this. Then, but in your slides, it's written it reduced to n links. So the number of links will be n into n minus 2 at the core layer, right? You can see the n
N
into n
into
minus
n
2
minus
n
1
links.
by 2, then it will be reduced to your n links.
For distribution switches.
So basically it is a combination of formula where you need to choose the element out of n, and order goes, order does not matter in over here. Okay, same as you can say your NCR formula. NCR, if you remember, n exclamation divided by n minus r exclamation into r exclamation. Okay, so it is like somewhat like that.
Okay, clear. Thanks.
Okay, so you can say given n nodes, if every node is connected to every other node, okay, except itself, the number of connections will be n into n minus 1 by 2. Now how you will prove it, that you are asking me. Okay, okay, no issues. So this was our layer technology. Okay, hierarchical LAN design model. Okay, now we'll move to something known as enterprise network option architecture options. So we are having uh, multiple options are available for building the campus network depending on the scalability. Okay, we have two-tier design, which we have already seen, collapsed core. We have three-tier design. We have layer 2 access STP based. We have layer 3 access layer routing based. Then we have simplified campus design and software defined access. Okay, so see, uh, as we have seen the syllabus, I'll not go as per the syllabus. Okay, I'll teach by what I need to teach. Okay, but I'll be covering all the topics. Don't worry. So I'll not go by these that I'll cover the first chapter, then I'll go to the second chapter. I'll not do this way. I'll first complete whatever is necessary. Okay, whatever is important, and I'll make sure that I'll cover all the topics. Okay, so don't go that don't think that I will be going as per the syllabus. Okay, because it will be very confusing for you people. Like if I go as per the syllabus, I'll be studying over here the enterprise design model. Then here I'll be having a wireless module. Then after this first chapters, this first thing, I have to go all the way to the third chapter for wireless part. Then I have to go again for the wireless part. I have to go again down over here at the fifth chapter. So it will be not good. I'll go as per my, I've made something. Okay, so I'll go as per that. Like I'll go first with the architecture, then I'll start with my layer 2 and layer 3 technologies. Okay, I'll jump to my third chapter directly and I'll complete this layer 2 and layer 3 technologies. After completing this, I'll go to some virtualization topics. Okay, then in virtualization, after completing this virtualization, I'll come to wireless part. Okay, so this syllabus is a mixture of all the things. So I'll go step by step. Got it? So this SD access, software defined access part, I'll not show you right now. We'll study this SD access part when we will be studying about SD-WAN. SD-WAN will be starting about SD-WAN part, or you can say when we will start our automation chapter. That time we'll study this SD access part. Okay, so we have these many options in our enterprise network architecture. Okay, let us see one by one. Two-tier design or collapsed core, like we have already seen the diagram in the previous slides. Now it is used for smaller campus network that may not require a core layer for interconnectivity, as they may have multiple departments spread across multiple floors within a building. So we are having only one building and we are having multiple floors, and the networks are divided into multiple departments. Okay, so we can just have a collapsed core. Now two-tier design uses access and distribution layer only. Now in case the distribution layer also act as the core layer, that is connects to the southbound to the access layer. In the southbound direction, it will connect to the access layer. In the northbound to WAN, server farm, or internet or any network services. Okay. Now, prior to selecting a two-tier collapse core, a distribution layer future scale, expansion, and manageability factors need to be considered. Okay, like if we are designing any network, if we are designing for a small network, now we have to think about future. Like in future, if we need to scale our network, if we need to expand our network, then we need to design our network in such a way that if we need in future, if we need to have a core layer, then what we need to do? Okay, we can expand our network or not. Okay, like in this is the two-tier collapsed architecture. Okay, so The WAN edge block connects to the remote data centers, remote branches, and you can say or other campus network for connectivity to the cloud provider. So you can see my core distribution layer, my collapsed core is connected with my WAN connectivity, any WAN edge, any other branch office am I having in any other geographical locations, to the data centers or the server rooms. You can say it is connected to the ISPs, okay, with a firewall kept. It is connected to the network services, like if we have some wireless networks, or if we are having some external server, AAA server, external AAA server kept anywhere, or any CUCM that will be used in our collaboration part, okay, any telepresence manager. The data center and server room block is where business critical servers are placed. The internet block is used to regular internet access, e-commerce connection to remote branches, remote VPN accesses, and non-dedicated cloud provider connections. Okay, so I have distributed these things like what is the edge, what is WAN edge, what is data center, what is internet edge, what is network services block. Okay, so network services block is where devices providing network services such as wireless LAN controllers, you can say our AAA server is connected. Like I told you over here, you can see in the diagram. Is the diagram visible properly? Can you see, or I should take it anywhere else to enlarge it? The pixels are getting blurred. Okay, so you can see the diagram, how it is, how the connectivity is been made. Okay, full mesh, and for redundant there is much redundancy. Got it? This is something my collapsed core collapsed core design. Then comes my three-tier design. Now three-tier design, as we have already seen, the large networks require a core layer for interconnecting between distribution blocks. Okay, so might be a function of cabling requirements between the buildings, or might be a function of northbound connectivity requirements like WAN connectivity, internet data center, or uh, services. Okay, so here it will be internet and data center. Come on. Now, three-tier designs separate the core and distribution layer and are recommended when more than two pairs of distribution switches are required. So if we have three distribution layer switches, you need to distribute the core layer, you need to separate the core layer and distribution layer. Core layer will be comprised of pair of high-speed switches running layer 3 routing protocols, like example OSPF, EIGRP. Okay, at the core layer we'll be running our layer 3 routing. Now multiple pairs of distribution switches are typically required for following reasons. Now why we need to separate the core layer? Why we need multiple? See, when we need the core layer to be separated, when we have multiple distribution layer switches. So what is the need of multiple distribution layer switches? Why we need multiple distribution layer switches? Now, when implementing a network for a large enterprise campus composed of multiple buildings, where each building requires dedicated distribution layer switches. Okay, so in that scenario, we need a separate distribution layer switch. When density of WAN routers, internet edge devices, data center servers, and network services are growing to the point where they can affect network performance and throughput. So whenever my these WAN connectivity and WAN internet connectivity is getting increased, okay, so at that point of time, I need a separate distribution layer. When geographical dispersion of LAN access switches across many buildings in a large campus facility would require more fiber optic interconnects back to a single collapsed core. Okay, so whenever my access LAN switches are in different buildings, at that time I need a separate distribution layer switches. So these are the options when I need multiple distribution layer switches. Okay, and in this type of options, I'll be needing a separate core layer. So in this figure, you can see I have a different I have a building blocks of places in the network pins are each are using the hierarchical design model, and each block is deployed with a pair of distribution switches connected to the core. Okay, you can see the distribution layer switches are in pair. They are connected with the both of the distribution layer switches. Okay, both of the distribution layer switches, they are connected for redundancy purposes. The hierarchical design is more appropriate for north-south traffic flows, such as endpoints communicating with the WAN edge, data center, internet, or network services block. The data center blocks is using the newer spine leaf design. Okay, data center is using the spine leaf design over here. You can see I have the spine layer switches, I have the leaf layer switches, and on the these are the leaf layer switches and these are the spine layer switches. All the leaf layer switches are connected in full mesh with the spine layer switches. Okay, these are my server farms, or you can say my devices that are connected with the spine layer switches. Okay, sorry, the leaf layer switches. An alternative to the three-tier design when the traffic predominantly east-west between the servers within the data center. Understood three-tier design? Three-tier design. Then we have layer 2 access layer. Now traditional LAN design uses layer 2 access layer and layer 3 distribution layer. Okay, where the you can say the distribution layer host default gateways for end stations. Okay, distribution layer hosts the default gateways for the end stations. Now the distribution layer is the layer 3 IP gateway for the access layer host, you can say. Now whenever possible, it is recommended to restrict a VLAN to a single access layer switch to eliminate topology loops, like what we use to we have studied at the CCNA level. If we want to stop any loops, like loop in the layer 2 network causes STP to block links. Okay, so redundant uplinks from access layer to distribution layer remain unutilized. So to restrict a VLAN to a single switch provides a loop free design, but at the cost of the network flexibility, because all the hosts within the VLAN are restricted to a single access switches. Okay, so recommendation is to limit a VLAN to an individual access layer switch only. So loops can be removed by using layer 3 links between the distribution link switches. Okay, now might not be possible if VLAN services need to be span between the multiple access layer switches, you can say. Now some of the organization that the same layer 2 VLAN be extended to multiple access layer switches to accommodate an application or services. The looped design causes STP to block links, which reduces the bandwidth from the rest of the network and can cause lower the network convergence. So in this figure, you can see the layer 2 designs, okay, loop free with one VLAN per access switches, okay, one VLAN per access switch, and looped topology with VLAN spanning access switches. Okay, so the figure illustrates a loop-free topology where a VLAN is constrained to a single switch, as well as a looped topology where a VLAN span multiple access switches, the looped design causes STP to block links. So you can see the loop design is blocking the links. It is blocking the links. When we use the layer 3 link between the distribution layer switches, it will not block the links. Okay, loop free topology and loop topology. Now with the access, with the layer 2 access layer switches, distribution layer switches, we can are as I told you, they are the default gateways for end hosts. So here we can use first hop redundancy protocol. Okay, should be between the distribution switches to provide default gateway redundancy, like we can use HSRP, VRRP, GLBP. These are the first hop redundancy protocols. Okay, so at the CCNA level we have studied about HSRP. CCNP level we are only having about HSRP and VRRP, but I will be teaching you about GLBP also, like how GLBP work, what is the configuration of GLBP. There is nothing in the blueprint, there is nothing about GLBP given. We only have the configurations of HSRP and VRRP. If I show you this, the syllabus over here, see HSRP and VRRP. You don't have anything about the GLBP, but don't worry, I'll show you the GLBP, how it works, what is the difference between HSRP, VRRP and GLBP, and how it works, what is GLBP, how to configure GLBP. Okay, so this was our layer 2 access layer. Then comes layer 3 access layer. What is that is known as our routed access. Routed access. Okay, so as the name only says, routed access is an alternative configuration in which layer 3 is extended all the way to the access layer switches. Now in the diagram you can see layer 2 access layer STP based will block my links. Okay, now this is my layer 3 access layer. This is the design of layer 3 access layer, the second diagram. Okay, and this is something layer 2 access layer STP based. Okay, so in this design, access switches act as a full layer 3 routed nodes, providing both layer 2 and layer 3 switching. And the access to distribution layer 2 uplinks trunks are replaced with layer 3 point-to-point routed links. Okay, so the trunk links are replaced with the point-to-point routed links. Now, consequently, the layer 2 and layer 3 demarcation point is moved from distribution switch to access switch, as this you can see over here. Previously the layer 3 was running over here. Now the layer 3 is running between the distribution layer switch and the access layer switch, and the layer 2 functions are done below the access layer switches. See, the routed access to distributed blocks design advantages over the layer 2 access layer design. So we got some advantages, like there is no need for first hop redundancy. Why we need first hop redundancy? To make the to have a redundant part, to have a backup to reach over the layer 3. So no need for redundancy. It eliminates the need of FHRP protocols such as HSRP and VRRP. No STP required because there are no layer 2 links to block. The design eliminates the need of STP. Increased uplink utilization. Both uplinks from access to distribution can be, you can say they can be used, increasing the effective bandwidth. Okay, for the end users. Easier troubleshooting. Now it can offer common end-to-end troubleshooting. like we can use ping command and trace route. Faster convergence. It uses faster convergence routing protocols such as EIGRP, OSPF, okay, between the layers. So these are some advantages that we have in our layer 3 access layer. Then we have simplified campus design. Okay, so it relies on switch clustering such as VSS, okay, virtual switching system, and stacking technologies such as you can say stackwise, okay, in which multiple physical switches act as a single logical switch. So clustering and stacking technologies can be applied to any of the campus building. Now clustering is something combining the access layer switches, you can say the work of the access layer switches or somewhat. Stackwise means making stack, making layer, or making a bundle, you can say. In other words, making a bundle of the layers. Okay, so if we use this type, using this type of offers some advantages like simplified design. By using single logical distribution layer design, there are fewer boxes to manage. Okay, so I'll show you the diagram which reduces the amount to spent on the ongoing provisioning and maintenance. No first hop redundancy protocol required. It eliminates the needs of first hop redundancy protocol because the default IP gateway is only one single logical interface. Reduces STP dependence. Because ether channel is used, it eliminates the need of STP, layer 2 access design. However, STP is still required as fail safe in case multiple access switches is interconnected. So I'll show you the diagram over here first. So this is something my simplified access campus design. Okay, like if we are having some distribution layer switches and we are having some access layer switches. So what we can do, we can use VSS and we can combine these two and we can make a VSS thing. Okay, and we can use VSS with stackwise to make my access layer switches. Okay, here we will be having some ether channel running over here. Okay, stackwise logical layout for with VSS and stackwise, and this is logical layout with VSS, and this is my physical layout. This is my physical connectivity, and what I did, I combined the distribution layer switches with the VSS. Okay, and at the access layer I use some stackwise which will combine my access layer switches. Okay, so I'll be using ether channel between the connectivity. Increased uplink utilization. With ether channel, all the uplinks from access to distribution can be used, increasing the effective bandwidth available to the end users and endpoints connected to the access layer switches. Okay, then we have easier troubleshooting. Now the topology of the network from the distribution layer to the access layer is logically hub and spoke topology. Hub and spoke one-to-one connectivity, which reduces the complexity of the design and troubleshooting. Okay, then we have faster convergence. With ether channel, all links are in forwarding state, and this significantly optimizes the convergence time following node or link failure event, provides fast sub-second failover between links in the uplink bundle. So the convergence will be faster as we are using multiple links, we are using ether channel bundles. Okay, distributed VLANs. Now with this design, VLANs can be span multiple access switches without the need to block any links. Okay. So these are some advantages that we'll be getting if we use the simplified campus design. This is also one of the network architecture options, enterprise network architecture option that we can use. See, like this, we can use using the simplified campus design approach across all the campus block can provide an optimized architecture and ease to manage, resilient and more flexible with higher aggregated uplink. Like you can see in the diagram, you can see in the diagram what I've done. I've used VSS over here and over here, and at the access layer I've used some stack wise. Okay, so I'll be having only one logical connection for all the layers. Okay, between all the layers I'll be only having one logical connections. At the internet edge also you can use the VSS. At the network services you can use VSS. At the WAN connectivity you can use the VSS for the connections. Okay, SD access will be studying uh, later parts, okay, in our later lectures, as I told you. Got it? Forwarding architectures. Forwarding architectures in the sense how switch will forward the packets, okay, how the forwarding architecture works. So before going to the process switching, let me give you some difference between my CAM table and TCAM. Okay, so if I give you a difference between my CAM table and TCAM, now Cisco Catalyst switches use several different types of tables to assist in the switching process. So two of these types of tables specified memory architectures that we'll compare over here is CAM and TCAM. Now CAM stands for content addressable memory. Content addressable memory, and all of the models of catalyst switches use CAM tables for layer 2 switching. Okay, now as the data frames arrives on a switch port, the switch will learn the source MAC address. Okay, so correlating to the that traffic, and it's going to what is happening, it will correlate that traffic, and it's going to record those MAC addresses in the CAM table. So CAM table found in Cisco, why it is doing automatically, found in Cisco switches. What is happening? I think so it is due to my mouse. I'll just remove my mouse. Found in Cisco switches, found in multi-layer switches and routers, TCAM. Okay, TCAM. MAC address to port mapping in CAM table. In TCAM, we will be using ACLs, QoS, and other information for upper layer processing. Layer 2 technology, layer 2 forwarding decisions are taken care by your, you can say, CAM table. Switches can have multiple TCAM to boost performance. Okay, so now whenever, as I told you, as the data frames arrive to the in a switch, what the switch will do, switch will make an entry in the cam table. Okay, switch will make an entry in the cam table. Now this is done. So the next time if there is any frame destined for a specific MAC address, the switch knows exactly how to deliver that. Okay, and the switch port and it should use to do so. So it will make the entry like for which VLAN it is, the MAC address is connected to which port. Okay, and all these things. Now the entry recorded into the CAM table includes the port number the frame arrived on and the source MAC address associated with the frame, and also you can say the timestamp for the frame's arrival. Now CAM tables are large, but they are finite. Okay, they are not infinite, they are finite. So on a large network, it's completely possible to run out of the CAM table spaces. Okay, so that's the reason that the timestamps are recorded in order to manage the what are referred to the stale entries. Like if we have suppose a older entry, the older entry will be getting removed. Okay, as per the timestamp, the older entries will get removed. Okay, so now the addresses that have not been heard from a quite some time, you can say that the CAM table entries are automatically removed after the particular aging time. And by default, the CAM table entries that are idle for more than 300 seconds will be deleted. How many seconds? For more than 300 seconds, if any CAM table entry is there, it will be deleted automatically. Now this could be you can change this very simply from the global configuration mode on the switch, and with the you can say you can use the command MAC address table aging time followed by the number of seconds that you want to set the aging time. You can do it. Okay, now if the MAC address learned on one switch port suddenly appears on a different switch port, maybe someone's plugged their laptop from onto one port to another port, as an example you can say. Now the port, the MAC address and the timestamp are going to be recorded for the most recent occurrence. Okay, suppose the laptop was connected on port number 1 and I remove it from here, I connected to port number 4. Now it will record the most recent occurrence of the MAC address and the old entry will be deleted immediately. Okay, so now I will be having two entries. So the older entry will be deleted and the newer entry will be given a new timestamp. Okay, now the purge happens in order to avoid having duplicate CAM table entries. Otherwise, what will happen? The switch may be confused when it makes the switching decisions. So now, as we have already said, the CAM table can learn those MAC address dynamically from the incoming frames, so which is the default action. But you can also configure static CAM table entries as well. Okay, so during you can say CAM table lookup, the table will provide one of two results, either a true or false. So either the MAC address will be found in the CAM table or it will not be found in the CAM table. Now those are only two possibilities with the CAM tables. Now in the binary, in the in binary, this will be either you can say 0 or 1 value. So it's going to look for an exact key consisting of binary numbers during the table lookup process. Now another type of table is my TCAM. Another type of table is my TCAM. Now TCAM stands for ternary content addressable memory. Ternary content addressable memory. Okay, so some layer 2 switches will contain TCAM for quality of service usage, but primarily we see TCAM in multi-layer switches only. Okay, primarily we will see this in multi-layer switches only. Okay. If you think about a traditional layer 3 routing, one of the ways you can say that we control our traffic is through we can use some access, you can access control list. Now these ACLs will contain entries that will either permit or deny the traffic based on the rules, okay, that we will determine. So for example, maybe we have an ACL denying a traffic from a specific IP address. Now when the traffic arrives from that IP address, this traffic would evaluated against the access control list. And if matching statement is found, the traffic will be dropped, correct? So we can think of an access list as a very common function that uses TCAM. So it uses those ternary content addressable memory tables in the exact same way that we are talking about here. Okay, so they do that in order to perform packet matching using wildcard values. Now the TCAM is essential an extension of the CAM. Okay, but where the CAM can only return two results, either true or false, or match or no match found, the TCAM also have a third state called the any value, any, like we have in ACL, any value, or the do not care value. So during the lookup, this leaves the third value 0 or 1 and X. The third value is X. X is something is X is do not care value. X is a do not care value. Okay. Now these three values are where the table gets its name. Okay, as the term you can say ternary is defined as a mathematical value based in three. So instead of performing exact match searches, the TCAM can perform a broader search based on you can say based on some patterns matching and wildcards. Okay, now the entries in the TCAM have a particular format referred to as VMR, value, mask, and result. In the TCAM, we have three types of entries: value, mask, and result. Okay, the value refers to the pattern that is being matched. Okay, what is the pattern that is being matched? Which can be, you can say, IP address or protocol ports and so on. The mask refers to the mask bits associated with the pattern. Okay, so with the access list, we assign a wildcard mask to our entries. Now these types of masks are used in TCAM lookups in order to determine which bits are of interest to us, and the result or are numeric values that represent that represent the action which should be taken after the TCAM lookup. Now those can include permit or deny or QoS policing, next hop, forwarding, and so on in the mask. Okay, so we can connect a live interface and we can run the command. Okay, now this is something our TCAM. Okay, this is something our TCAM. Okay, so that's something a look difference about the CAM and TCAM. Okay, all the layer 2 Cisco Catalyst switches use CAM, while the TCAM is typically seen in the multi-layer switches and routers. So we do see some layer 2 switches for use of our QS quality of service enforcement, but by and large whether the switch is a layer 2 or multi-layer device usually determine which type of table is available on that device. Okay, so this is something my cam and tcam. Okay, so we'll stop over here for today. Okay, for today's lecture we'll stop over here. Then from tomorrow we'll start with process switching. What is process switching? How process switching works? What is fast switching? What is CEF? We'll study about software CEF, hardware CEF, then stateful switchover, how stateful switchover works. Okay, then we'll start our layer 2 technologies. Got it?
Okay.
Okay.